Hello everyone. Today we're going to be going over PyBullet and using that in a custom Python environment. And this is just going to be a quick start guide, the basics of PyBullet and using PyBullet. And this tutorial is not focused about training any agent on the environment that we're going to be building. It's just about making sure that we know how to get PyBullet set up inside of custom environment, and it's going to be very similar to just building a plain Python environment. And we're going to still be doing everything in Python. However, we need a few extra lines of code, and we're just going to be going over how we would do that and where we would do what steps. So PyBullet is pretty cool. You can go ahead and you can simulate a ton of different things in PyBullet. As you can see from there, it's just a physics simulator. And the documentation for PyBullet is available right here on pybullet.org. If you go to pybullet.org, there's a link for a quick start guide. And you can see, obviously, you can do crazy things inside of PyBullet. Lots of different things, lots of different assets that you can load into it and work with those and use those for training or whatever. But you can just go ahead and go to the PyBullet quick start guide, and this is where the documentation is for it. And you need to make sure you have PyBullet installed. You can just do pip install PyBullet, and it should be installed if you're using pip. And the functions that we're going to be going over from PyBullet just to get things set up is connect, disconnect, set gravity, load URDF, which stands for load universal robot description file, step simulation, get base position and orientation, and there are a few functions from controlling a robot that we're also going to be using, which is get num joints, set joint motor control array, get joint states, get link states, and I believe that is it for now. We're also gonna go over get camera image, but not this one. I think we're using we're not using get camera image. We're using the debug camera, which don't see where it is, but you guys will see it as we go over it. So we're just going to go over a few of these functions and why they're necessary to go ahead and build our own custom environment. So when you install PyBullet, it comes with PyBullet data. So if you just search in a browser for PyBullet_data, you should be able to find a GitHub link for PyBullet data. And this is just several assets that are ready to load inside of PyBullet, so you don't have to go ahead and build any individual object or asset that you would like to use it for, in your environment. There are plenty. It comes with a bicycle, it comes with a Panda, which is the robotic arm that we're going to be using for this. It comes with a gripper, humanoid agent, husky, which is like a little car kind of thing. It comes with the mini cheetah and many other different assets and objects that you can go ahead and load. And you just need to describe the file path as the file path is given in here. So for Panda, you go to Panda / panda.urdf if you want to load the panda. If you want to load the soccer ball, you can go ahead or if you want to load cartpole, you can just load directly cartpole.urdf. But we're going to go over all of that right now. So I just have some code open in my text editor, and for this example, we're going to need to import numpy as np, import PyBullet as p, and import PyBullet_data. And we're also going to import time because we're going to be stepping the simulation, and the simulation actually steps in faster than real time, so we're going to have to delay that by a bit by just adding a time delay using the sleep function. So it's very easy to go ahead and connect, get the environment set up in PyBullet. We just called p.connect, and we pass it p.gui, GUI. which gives us a user interface. And this is if we want to have like visuals of our simulation as it's happening. And if we don't, we could just type p.direct, and that will give us it will still be doing everything, but we're not going to be getting visualizations of it. So we could like I mean, if we're going to be training in faster than real time, because right now we're going to be doing it in real time for visualization, but if you're doing training, you want to train in faster than real time, so you might do it on p.direct. So it's p.connect, and it needs to know whether there's a user interface or not, so that takes p.GUI or p.direct. And we also have to call p.reset simulation, just to reset the simulation. And since we're going to be importing some of our assets from PyBullet underscore data, we have to pass p.set additional search path to PyBullet underscore data dot get data path. And this is actually all boilerplate right here. And we also need to create gravity for our environment. So it's a physics simulator, but so you can, obviously modify. So we have an X, Y, and Z values, and we could, change the gravity. It doesn't have to use Earth's gravity. We just set it right here to negative 9.8 because, that's the, I think, gravitational constant, or, you could use negative 10 or whatever. But it's, meters per meter square, or meter square. So we're just setting our gravity to Earth's gravity, and we're setting p.set real-time simulation to 0, just so we could be in charge of like stepping the simulation. So this is pretty much setting up the simulation or the environment for PyBullet. So once we've done that, we actually have a very let me go ahead and actually see if I can run that. So I'm gonna just go ahead and hit run, and should probably have it sleep. Copying that. All right. Let's have it for like 5 seconds. So you see, it's just an empty environment over here, and you could hit Control and drag around to see the environment. So it's empty, and there's nothing in our simulation right now. So we're gonna need to load some assets so we can work with them and information of the assets, the coordinates, the positions, orientation, everything, how they're interacting and not. So we're gonna load just a basic plane into the environment. This is just a ground plane. This is very customary because, since we're setting up gravity, if you don't have a ground plane, everything's just gonna continue to fall. So we need to load in our assets. And for this tutorial, we're gonna be using, like I said, our Franca Panda, our Panda URDF. So the way to load assets is you call p.loadURDF. You pass it the name of the file from PyBullet data. You pass it its position in space as XYZ coordinates, and you pass it its orientation as a quaternion, which is I genuinely don't understand what a quaternion in, but this is the default position for it, and a quaternion is just letting you know about the orientation of an object in 3D space. So if you want to know more about quaternions, look it up. And we also need to import our or load our robotic arm. So we're gonna do p.loadURDF, and we're gonna pass it the file path for the panda, which is franca_panda/panda.urdf, and we're gonna tell it just the position. We just want it, in the center of space 0, 0, 0, and orientation is default upright orientation, and we use fixed base is equal to true as an argument because so each URDF, it's technically a set of links, and there's a base link, which is like the initial link, and so when we're applying forces to an object, like if you apply forces to a cup from the side, it's going to knock over the cup. And same thing goes for any object that we have. However, if we like glue the bottom of our cup to a table and we apply a force, it's not going to get knocked over. So, you know, we want to fix space for certain objects, and for certain objects we don't. But for the arm, we don't want it to be falling over as it moves. So we're going to use fixed space is equal to true. Okay. And there's a debug camera that comes with PyBullet. So yeah, so we're just gonna have, so p.loadURDF returns a single value, and that's just the index of, you know, each asset. So this is the 0th asset, and this is the first asset because we loaded this first and we loaded this second. So we want the camera to be focused around our Panda robotic arm. So we're just going to call our object to focus our target ID, so the value of this specific asset. And we're going to see why right here, just down here. So we're just going to run this for like a couple hundred time steps. And so this is going to be like 2 seconds or 3 seconds of simulation because we're only stepping like 1/100th of a second. We're only giving it like that much time in between, you know, steps. And we're going to ignore this for like just 30 seconds, like this commented out code, and we're going to come back to it after we run this code now. So for step in range 300, we're just going to determine the position of our target ID by using p.getBasePosition and orientation, and it returns our position as one value and our orientation as the other. And we don't need the orientation right now, so we're just going to throw that away with you know, using an underscore as a variable. So now we know the position of focus that we want the camera to be on. So we're going to now set the camera to be focused on the focus position. So we do p.reset debug visualizer camera, and it just wants to know how far away is the camera from that position of focus. The yaw and pitch of this, which is just rotations around like X, Y, and Z, like, you know, yaw, pitch, and roll kind of thing. So this is gonna, since we have a camera pitch of -40, we're just gonna be looking down on it slightly. And the target position of where we want to be looking at is the focus position, which is the position of our robotic arm. And then we're gonna call p.stepSimulation, even though we haven't actually done anything yet. And we're gonna have it time.sleep, and you'll see why we have these 2 lines in just a minute. So I'm just gonna go ahead and hit run very quick, and you're gonna see the robotic arm load for 3 seconds, and then the simulation is gonna end. Okay. So there's a few things that we can, several of the functions that I said we're gonna go over. So you guys saw what the robotic arm looks like, and that, you know, there's joints and links, and that like the base is a fixed base to the ground. So each of those joints and each of those links has specific information. Like a joint might let you know what torque has been applied to it, or you know, what its position is in radians, because, you know, if it's like that or like that, you know, the angle or position of a joint, of any specific joint, is changing if you're applying forces to it, or there are forces being applied to it. So we want to be able to find that information. So for updates to our state, or for updates to our observation. So we need to query that information. But first we need to do a little bit of digging and find out exactly information about any one state or joint or whatever. So like for example, I could do p.getNumJoints, and this is just going to let me know how many joints there are inside of you know, whatever ID of whatever asset I pass it to. So I'm just going to pass it target ID, which should be 1 anyways, and I'm actually going to comment this out for a moment, and it should have printed for us the number of joints that we have, which should be guess we'll have to go over this in the notebook. But anyways, so this is supposed to have 12 different joints, and it was, oh, I didn't print it. That's why it didn't pop up. So this is supposed to have 12 different joints if we, from the return value of the number of joints that it has. So we're just going to query information for a single joint, which is the fourth joint. Okay, and yeah, we'll actually come back to this after we go over the tutorial that's in the Colab notebook. Okay, so I apologize for wasting like the past 60 seconds. Anyways, so in Colab, we have to make sure we have it installed. Okay, so we do pip install PyBullet. You know, make sure we have like the exclamation mark because we're doing an install in Colab notebooks. And we're going to go over setting up the environment. This is stuff we just did a moment ago, and we know how to load the assets. Okay, I'm going to play all that. And we're going to go ahead and find how many. So this is all copied code from the other one. But you see here, since we're in Colab, and we're just going to do p.direct, which is the only difference. Just because you can't get the GUI in Colab right now. I mean, you have to do configuration, which we're not going to do for this tutorial. So we're just going to use p.direct. So our target ID is the asset value of our gripper arm. So we see it has 12 joints. Okay. So if we want to get the information for each joint in for this one specific asset, we know the number of joints it has. So we could say for I in range, p.get number of joints of target ID, so the number of joints that it has. So for I in range 12, we're going to print p.get joint info, and we're going to pass p.get joint info takes two arguments. The first argument it takes is the value of the asset that we're searching for and the value of the joint that we're searching for. So we're always going to be searching, getting the joint info for our panda and for whichever joint for all 12 joints. And you see it returns many values, but we're only going to be concerned with the joint type in general, and which is we've listed out each joint. Each joint has a name, and each joint has a type of like what type of joint it is, and that would affect how you apply forces to it and whatnot. And it will also have a maximum and minimum angle that the joint can move to. So the maximum and minimum values are like at the 8th and the 9th index. So the lower bound that any joint can move to, we can get that by just querying joint info of any specific joint and getting the 8th index. And the upper bound, which is J upper, we can query a specific joint on a specific asset and get the 9th value, index the 9th value, and that's our upper bound. So we can see that for our second and our fourth joint, that the upper and lower values are the same, 2.96 and negative 2.96. So we're going to go ahead and use those when we're stepping our simulation in just a minute. And so if we want to actually apply forces to those joints, so to apply forces to those joints, you're going to have to be giving it, or to change the angle of those joints, we're going to have to say we want to move this joint from its current angle at whatever to a new angle at some other value. So what we have to do is we have to step our environment, and we have to provide new positions or angles for our joints. So it's pretty intuitive. So I'm just sampling some values from using np.random.uniform and just sampling a new target position that I would like the joint to move to between the values of J lower and J upper. And I'm doing that for the second joint and for the fourth joint. And those are just going to be our target position values. Okay. Now the way that we apply forces to change the position of these joints. So what we have to do is we take p.set joint motor control array. So what this function takes is it takes an an ID value or asset value, you know, it needs to know what asset we're going to be controlling, the specific indexes of the joints that we're going to be controlling, what types of control we're going to be applying to the joint. So there's, by default, there's velocity control, torque control, and position control. But for this tutorial, we're just keeping it simple and using position control. So we'll try to move to that position within a single step. And we have our target positions, which is the new target positions for each of those joints. So the new target position for our second and the new target position for our fourth. So we can control multiple joints on a single asset using set joint motor control array. Okay, and then we're gonna call p.step simulation. And so I'm just gonna go ahead and run this. And okay, so we're not really logging any information right now. So we can go ahead and, like I said, we can find the joint states. So I'm going to go ahead and change that to joint states. And you'll see as we're applying different forces using p.set joint motor control array, with each step, the value of our joints that are getting changed are obviously correspondingly changed. So you can see that they're getting changed as we're applying different positions to them. So these are the values for the second joint. These are the values for the fourth joint. And yeah, so this is for the joint information. But you know, the joints are the positions in between links, and we can also query information for our links. Whoops. So we can also call p.get link states, and we also pass it our target ID, which is, you know, the ID for the arm and the specific joints, or well, this is the specific links that we want to track. And the values that get returned between joint states and link states are different, because one is the actual, you know, position and orientation of the link, and the other one is like the angle of the joint and the forces being applied to it. You can go ahead and check the documentation for more information, but you'll see we're going to be getting different values back. So you see the way that the information looks is much different, because now link states is providing you know, position, orientation, world reference frames, things like that. Okay, so let's go ahead and now incorporate PyBullet into our custom Python environment like we've done in other tutorials. So we're gonna go ahead and actually get rid of that, because we're doing it direct inside of Colab. So we're doing it direct inside of Colab, so we can't do the visualization because we're using p.direct. So there's no need for the debug camera visualizer because we can't see it. Okay, so first thing we're gonna do is declare an environment. I'm just gonna call it arm environment, and inside of our initializer function, we need to initialize our state and set our step counter to 0. So inside of our initialized state, we're just going to be doing the same thing that we did you know, twice already in this tutorial. We're just calling p.connect to set it up, p.reset simulation, give it the path for so we can load assets from PyBullet data. We're going to set up gravity. We're going to load specific object instances, and you know, that's our arm, this is our ground plane, and we need some kind of state. So just since this is a super simple tutorial, we're not even training on it right now, the only information that that we're going to be monitoring is like, where is the link position of like one of the very last links. So for our panda, link 9 is like pretty much the hand. So we want to like monitor where the hand is. So we just want to find out. So if we call p.get link state on the ninth link, we're going to be getting the hand information, and you guys saw that it returns a ton of values. So we're actually going to be querying only the 0th index for each of them, which is just going to be 3 floating values for the position in 3-dimensional space. So this is going to give us, as our finger position, three values for the position of the hand in three-dimensional space, and that is going to be our observation. So our finger position or hand position, we're just going to put that into a NumPy array, and we're going to return that as an observation for setting up our environment. Okay, and then the reset function of our custom environment, we do the same thing that we do in the other ones. We call p.disconnect. Well, that's specific to this because we have to disconnect the simulation to restart another simulation. So like things don't get confused behind the scenes. And we reinitialize our state with self.init state and reset our step counter to 0. Okay. Okay. And then the only thing that is left is our step function. So for this one, we're just going to be running this randomly. So we're only going to be giving it a single action, and we're only going to be stepping on the fourth, taking action on the fourth joint. Okay. So we increment our step counter, and then whatever action we get, which is going to be like a floating point value, just from NumPy, as you guys saw in the other tutorial, we're going to call set joint motor control array on our panda arm, and we're going to be modifying the fourth joint, and we're going to be doing position control type of action on it, not velocity control or torque control. And the action that we get, the new target position for our joint is going to be the action. And so this, we could just call this new pause because we're inputting it as the new desired position. So we could just say new pause. Okay. Then we're going to step the simulation, obviously. And, because we now applied a force to our arm, the finger position is going to be moved. So that's going to change our observation. So we go ahead and query our arm for its to find out where the finger position has moved to. And we're going to go ahead and change that in a second. So we need to check for our termination condition. So and this is just arbitrary, if the environment has stepped through more than 50 steps, call reset, update the finger position, return the finger position to the state right here. And since we're not actually taking any actions and there's no goal for this randomly moving robotic arm, I'm just returning a reward of -1, which is an arbitrary reward. What you guys will see in a future one, that future tutorial, if it ever comes out, is that like a reward could be the finger position, the difference from the target position. If you're trying to get the hand to move to a target position to pick up an object or something, it could be like the distance, or well, not the distance, but But anyways, this is just an arbitrary reward. The done flag is set to true because this is termination condition. And I guess actually, I do apologize. I probably could have actually removed this entire thing, but I didn't. And now we're going over it. So we have to make sure, we got a new finger position. We need to make sure that we update our observation, which needs to, based on that new finger position, which updates our state, and return an arbitrary reward for this random environment. And so that's how you set up the environment. It's very simple. And there's really not much to it. And I'm doing it very simple because, we could modify every single joint in the arm, but that would look like a lot more code. And we'd have to pass, if we were to pass, just the same two joints that we had up here, we'd have to the step would have to take new position for the second joint and new position for the fourth joint. And I didn't want to make that very confusing right now. So we're just going to test it out super quick. So we're going to instantiate our arm environment and call that env. And so we're going to stay for step in range 500. We're going to go ahead and pick a random action, and this is going to be new pause. I like new pause a lot better for new position. Okay. And we're going to get a new position based on our upper and lower bounds that any one joint can move. and we're going to go ahead and step the environment on that, and it's going to return to us, you know, the reward and whether we're done. And it's also going to print the updated environment.state, and we're going to click p.step simulation. And so we're going to go ahead and print. So you see that the state is getting updated anytime we apply an action to it, okay? Because, you know, we're getting different values for our observation. And you can also see how it's affecting the links corresponding. So, and actually I'll have it return both values because, you know, oops, that's not what I wanted. Let's see if that affects anything. Which, oh, I just hit Control Shift B, which is not how you run things here. I don't know why that's doing that, to be 100% completely honest, but we could also do so we're getting some information for our links, for the links 2 and 4, and we can also get joint information as well, so joint. Okay, so we're gonna go ahead and hit run, and you'll see that the joint information is also updating. Okay, so we're just gonna ignore this for now, sorry about that. A few hiccups in this walkthrough. So we didn't get to visualize it. We just got to see like the updated state output from here, just what the new state would look like as far as where the finger position had moved. So let's go ahead and visualize it. This is, we're just gonna now step through it without the environment, just so you can visualize it, okay? So all we're doing is we have our lower and upper bounds for a specific joint, and we're just gonna be calling, and for this one, since we're not using the environment, we're just going to be affecting 2 joints at the same time. So we're going to be affecting the second and the fourth joint at the same time. And they both have the same upper and lower bounds. So we're just going to be sampling a new joint position for our second joint, a new joint position for our fourth joint, and passing that to joint motor control array on our Panda arm for the second and fourth joint. We're going to be doing position control, and the new target positions are the positions that we randomly selected. So I'm going to go ahead and save and run this environment. Maybe I'll do it for, no, 300 seems like fine. So it loads it, and it looks very erratic, but that's because we're getting completely random movements because we're just using np.random, and we don't have an agent that's actually trying to maximize some objective. So just running it one last time, you see that it's just totally random actions on the second and fourth index, which is making it flail like super crazy. But that is how you would go ahead and create an environment. Go ahead, take this environment and try to modify it so you can, you know, modify multiple joints at the same time, or try it on separate agents. We will go over agents that can, you know, try to solve this environment, or, you know, at least receive higher reward in this environment than a completely random agent. But that will be for tutorials such as advantage actor critic in a continuous space, and potentially, if I ever make the video, soft actor critic. But, you know, those will be for future tutorials. I hope this was helpful to some degree. Make sure to read the documentation for PyBullet and get familiar with it. To be completely honest, like, this is the most important part. So it's like 40 pages, and of those 40 pages, there's like 20 or 30 that maybe like really matter, you know, and that you might be using for your specific whatever it is you're doing. So like I said, yeah, I hope this was helpful. Like, comment, subscribe. Thank you for watching, and we'll see you guys all at some other time.